Yeah, kind of continuing from back, was it, well, I guess Tuesday's session, when we were doing section 40, like talking about big data. We talked about a few things about big data, like parallel processing versus distributed data, some tools. The one that curriculum really talks about is Spark. Spark is very popular right now. We talked about how that's different from one of the older systems called Hadoop. It's not necessarily like, when I say older, I don't mean like, oh, it's not used or, you know, it's inferior. It does a fine job for what it does, but Spark definitely is more like the new kid on the block that does a pretty great job, mostly because it handles everything in RAM and memory, versus Hadoop had to use what's called the hard drive file system. So there's some advantages to using Spark. And usually, I think in the curriculum, we actually talk about using PySpark. If you guys have, I've seen already a couple people trying to like get it started through Docker and everything. It is quite a process. I will say is that you don't necessarily need to have it to do this for the Mod 5 project. So if you feel like you're really getting like kind of frustrated on that section 40 trying to implement Spark, know that you can kind of like put that offside, and we'll definitely talk more about it as well. So I don't want you to get caught up and be like, oh no, I can't do Spark, therefore, you know, I can't do the project. Okay, but I did want to show you guys a little bit of overall like how we would do something called MapReduce, which is more of a philosophy of how you code versus an actual like strict tool. That was kind of confusing because there is a MapReduce kind of program, so it kind of makes it a little confusing like which one you're talking about. But I'm going to show you guys the overall concept of MapReduce. All right, so let me go ahead and start sharing my screen. And this, all the notebooks I have right now should be up to date in GitHub. But if you guys do find at some point and you guys are using that fork and it doesn't look like right from like what we're showing today, definitely let me know so that I can make sure to make that push. Okay, so, all right. So let's see here. I'm gonna go ahead and pull up our MapReduce. I'm gonna move this little guy. You can't see that, but all right, oops, wrong one. So we talked about a little bit about distributed and parallel computing. I'm just going to kind of quickly review that, just kind of look at this. Is we talked about how distributed computing and parallel processing is very different from sequential. So what we've been doing so far really has been sequential programming. Basically, it's on your computer. There's no distributed network. Basically, you can treat everything on your own computer, right? This kind of sequence. But now what we're going to start looking is like, how can you distribute this and also do it in parallel? And the idea here is that parallel can be done out of order. Basically, it doesn't have to wait for these previous steps before it can start doing the next thing. So I'll give that kind of analogy to our concept of MapReduce. So this is where MapReduce, this is actually the same, I think it's the same diagram that the curriculum shows. So I just went and pulled it from there. And I think sometimes it can get a little confusing exactly what's going on with MapReduce, like what are these exact steps? So I'm gonna kind of walk this through a little bit. But first I'm gonna kind of start off with a little analogy with this. So one thing I will kind of phrase this as, well, okay, when I was teaching, one of my biggest like banes that like, you know, well, actually, I think most teachers would hate this, is grading and then passing back papers. Especially when you had like many students. Like sometimes I would have literally over 200 students for like a class, not at the same time, but I had to give back their papers. They're all the same assignment. One big thing I had to do was alphabetize. And it sounds like, you know, like, okay, like that's just what it is. There's a whole, like, I can go, like, it's kind of funny. I went through this whole process of like how you could alphabetize, like through something called merge sort and stuff like this. And it blew other teachers' minds and stuff like this. But the main idea here is like, well, okay, if I had 200 papers, or let's say, let's go even higher, let's go 500 papers, it might take me a long time for me as a single person to be able to like order all the papers through, especially like there were situations where we had standardized testing. And so one thing we could do is we can, if you actually use an algorithm like something like merge sort, if you can each get like smaller packets of like each, let's say you have like a packet of like 50 papers and you have each of those sorted, you can actually combine them together relatively easily without having to like reorder everything. So basically if I give like, split up my stack of 500 papers and split it up, so it's like 50 papers per like, you know, teacher. So it's split on like 10 different teachers. If we each sorted those relatively quickly, we can then combine them together really quickly. So that's actually really similar to like how parallel processing would work. So the idea here is I'll kind of use that analogy as I walk through MapReduce. So what MapReduce basically has 4 main steps. And usually we really talk about map and reduce, but there's some substeps here. It's called split and shuffle. So ideas here we had start off with some big file, right? Some big amount of data. So this is what like the curriculum has, like a zoo file, so list of animals. And what they want to do in this case is take count how many times lion, tiger, wolf, or whatever animals in there, how many times does that occur? Okay, so you can imagine trying to do this, like classic programming. You'd go one by one, counting how many times it goes through. But we can actually distribute this out and make it in parallel. So the way MapReduce works is the first step is splitting, which seems kind of obvious, like what this does, but the splitting basically takes this different data and splits it up to each computer. So you can imagine each of these rows right here are a different computer. So each row is a different computer or different worker. Okay. So basically say, okay, you computer A, you're going to get lion, tiger, and wolf, that first line. The second one, the next computer is going to get lion, giraffe, and go on through that. So one thing to note is that it doesn't have to be split up equally, or it can just be equal enough. This would be equivalent, like if I'm talking about like my papers, I have 10 other teachers, I would just take, what looks like about 50 and give that to, teacher A, and give another 50 to teacher B, and so on until we get split up all the papers. Okay. The next part is basically this mapping section. And this mapping basically is kind of like the really simple ordering, if this makes sense. So in this case, we're just basically saying, from lion, tiger, and wolf, we're saying, oh, there's one lion, there's one tiger, there's one wolf. So the key point of mapping is that we're going to have a key and a value pair. And so in this case, the key is the lion and the value is 1. This is important because we'll later take this on and combine these together in our reduced form. But the idea here is just having each computer just map each part. This is where my analogy might not be exactly accurate, but you can kind of imagine this being like if we had a stack of 500, maybe we have like grade 6, grade 7, and grade 8. So you can kind of imagine is that we're essentially saying, okay, like, each of these are going to go into grade 6 area, grade 7, grade 8, since basically those ones only have to be organized by themselves. Okay. So everyone follow me so far? We're doing split and map. Okay. This is where I think it gets confusing when we say the next step is shuffle, which really doesn't make sense in my mind. I still don't understand exactly why we call it shuffle. It really, in my head, should be called reorganize. So the idea here is that we basically take these values that we've already mapped to, and we pass it on to basically organize it to be ready to be produced. So you can see here, basically all the giraffes go to this one computer. So basically this computer says, hey, I want everything that's a giraffe. And basically all these other computers will pass the giraffe to this computer. And the same thing for, there's like, oh, I want all the koalas, and I want all the lions, and I want all the tigers, and I want all the wolves, okay? This is where there's a little bit of behind the scenes. There's essentially something like a resource management system that's kind of like conducting all of this behind the scenes. It says, okay, computer A, you're gonna get all the giraffes, or you say, oh, get all the giraffes until you hit your memory limit or something like that. So note that in this scenario, you can see all the animals are in one computer each. It's possible where you might have koala and tiger together, or you might have a giraffe, and then maybe there's so many giraffes, another computer has giraffes as well. Okay, and this is kind of like, if you imagine like me, like this is my analogy, like isn't perfect, but like you can imagine like over in this room, like with other teachers, say, okay, teacher A is gonna get all of, 6th grade. Okay, you're gonna get all of 7th grade, you're gonna get all of 8th grade. So basically are sorting it out, saying 6th, 7th, 8th, and then passing it over to each one. Okay. So this is where it's like, okay, we got all these parts. And this is where the real like magic, not magic, but this is the real work happens, is the reducing section. So the reducing section basically takes whatever the computer has and reduces it down to one key value pair, okay? Or potentially multiple key value pairs. But the point is that it reduces this large amount of information down to its central information. So in this scenario, like, or my analogy of like teachers, this is when the people actually start sorting alphabetically. So the idea here is like maybe this person already has all of 6th grade, or maybe this person has half of 6th grade and this person has the other half of 6th grade, and they, what's it called? They order ABCs, for their group and stuff like that. They're reducing it down to like what it's supposed to be. In here, from the curriculum, you can kind of see basically they just count up all those parts. In this case, each key basically gets graphed over into counting a total of whatever that is. Okay, everyone follow me so far? Okay, and so once this has reduced part, basically each computer reduces to their individual parts, finally gets aggregated to the final result, and this basically gives us the full result of whatever our goal was from the very beginning. So in like my teacher analogy, it's like basically having each 6th grade, 7th grade, 8th grade, or whatever grades you have in alphabetical order. In this analogy here, or in this scenario here from the curriculum, it's taking all the words, all the different animals listed, in counting out how many times those animals occur in the list. All right, cool. So the main thing to remember on MapReduce, which again, I think adds a little bit of complexity of like why it's called MapReduce, but still it's the split step, the map step, the shuffle, and then reduce. Okay, cool. All right, how does it sound for everyone? Sound decent? Any questions? Okay, cool. Yeah, it makes it sound really simple. I don't know. Sometimes I think it can sound really simple, and other times it can look really complicated. So you might look at this again and be like, wait, I don't understand what's going on. But the main thing to know is that basically each step has a distinct like goal. Like you're not doing all of it at once. You're kind of like splitting it up. The main steps are basically passing along. And this is where it's really important to note when distributed systems make a lot more sense than having a single system. So if you imagine like, I like using my like teacher analogy thing, because imagine I have to pass out each of the papers to the different teachers, and me organizing 500 or more papers in alphabetical order and by class, that can take a lot of work for one person. But if I only had like 30 papers, it wouldn't make sense for me to get 10 other teachers, collect all of my 10 other teachers, pass out my information, have them do the split, have them do the map, have them do the shuffle, and then reduce it, whereas maybe they have only 3 papers to organize. It'd be faster for me just to do it myself. And this is where distributed systems make sense. So each of these steps have a little bit of extra like work you have to do. But if you're able to split it up significantly amongst many different things, because you have so much data, it might be more efficient that way. Okay. So here's another little diagram that I found online that kind of, I like using these colors. In this case, it's red, green, blue. So basically you have a mixed up order here, and you can imagine this node 1, node 2, node 3, each being its own computer. And essentially it's like, okay, here's your first half, you know, your first third, here's the other person's third, the other person's third. They organize it into, like, in this case, like this is the split step. This would be kind of like the mapping step, where essentially they go into splitting up into different parts. Like, oh, okay, here's all the reds, here's the blue, here's the greens. And basically this, what's it called? Going from here to here is the shuffle, which again, super confusing because it's not really shuffling. It's kind of like the opposite. It's the reorganization step. And basically, okay, this computer's only getting green, this one's only getting red, this one's only getting blue. And then they reduce that together. In this case, there'd be some extra computation and then combine at the very final step. Okay. Cool. One quick thing to note, because this kind of shows like map, shuffle, reduce. I did technically edit this a little bit, where I think originally this had like split, map, shuffle, reduce, which kind of confuses me because this is the real step right here. It's kind of like, this is the splitting step, this is the mapping step, this is the shuffle step, and this is the reduce step. Okay, so just know if you see this in the curriculum, it's going to be slightly like where splits here, map and shuffle and reduce. So, okay. So again, these are just little reviews, right? So I won't go through it again. Split, assign each worker. This is a mapping set. Remember, the big thing about the mapping is creating a key value pair. So basically there's a key and a value, and that's going to be really important. And in Python, we call those just tuples, right? Shuffle, you reorganize it, and then reduce, basically you combine it together. So you take whatever it was mapped over essentially and reducing it down. So usually the reduce step is relatively simple compared to starting from the very large data set. Okay. Everything sound cool? Yeah, all right. So this is my challenge now to confuse you guys even more. No, this is where I give you guys a little bit of coding part. And this is where I didn't use PySpark because I don't think you guys are as familiar with PySpark, and I didn't want to add that extra complexity in understanding what MapReduce is. Okay,